And so in this unit, we're going to be looking at this idea of the rate at which a reaction occurs, also known as the kinetics of a reaction. Now, if you stop and take a moment and just think about that idea, the rate at which a reaction occurs, it sounds to me, in order to understand how fast or slowly a reaction is going to occur, we're going to need to take into account time. And that's a concept that so far this year we really haven't spoken into. At no point have we ever mentioned, so how long is this going to take? At no point have we figured out or determined, so it took 10 minutes or 5 seconds, or it was fast or it was slow. We've said reactions have occurred. We've said reactions have released energy or absorbed energy, but at no point have we said, so how long is this going to take? And in order to do this, this is what we're going to refer to as kinetics. And as we stated, this is where we're going to start learning about how much time, and we're going to be bringing time into a lot of our chemical processes and into our equations. Since this is going to be a lot about this idea of time, that means that our equations are going to be introducing variables that we haven't really seen before. So we're going to have to be talking about a concentration, but not so much a concentration by itself, but how that concentration changes as a function of time. Right? Now, some of you, depending on your level of math, may have heard that differently. Some of you might have heard it as, okay, so if I have a change in concentration, that means that that's going to be delta for change, right? And then a concentration, let's say, of the substance, let's call it A, as time changes, right? Delta T. And there's nothing wrong with this statement. In fact, I would argue that at its core, this is what the change in concentration is going to look like. How quickly a substance disappears, how quickly a substance appears, right? Same thing. The snag that we're going to run into is that if I keep this very simply, as I've written it here, then what happens is that to me, this looks a lot like some final concentration minus some initial concentration. And that's going to be over some final time minus some initial time. And while there's nothing wrong with that, yes, that is true, that is by definition what we're talking about, this unfortunately produces a very linear relationship. So what I've just described, if we were to graph it out, would basically look something like this, where as time passed, so this was my amount of reactant, let's call it amount of reactant A, as time passed, we literally saw that bloop, 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 right? The amount of A, the amount of our reactants, is decreasing as a function of time. Here's the kicker. Rarely do reactants, or for that matter, rarely do reactions proceed in a linear fashion, meaning it is rare that when we look at the slope of the line, that we find that the slope or the rate at which the reaction occurs is constant. This is not the norm. It can happen. There are some equations where it does in fact play out just like this, but it is the exception to the rule. Typically, when we talk about the rate of a reaction, it's going to look more like this. Because what's happening here is that if you look closely, this is now going to be some type of curve. And what this tells me is that initially reactions start off really, really, really fast. And as time passes, they seem to be slowing down. Now, this is the more common slope, right? This is the more common rate of a reaction. And so when students look at this, they're like, well, wait a second, this is still the concentration of our reactant. Again, let's call it our reactant A. This is still A changing as time passes. Why couldn't this just be delta A over delta T, right? And as we said a moment ago, that, well, this would produce a very linear, straight line, a direct relationship. Since that is not the case, and again, depending on your level of math, remember that I said it was the change in concentration of A as a function of time. And so here's where I'll introduce a little, just a minuscule of calculus. Instead of saying that it was change as in delta, I could say that there's an infinitesimal small change in concentration of A, as we have the most infinitesimal small changes in time. And so this is the beginnings, right, of what we refer to as a derivative in calculus. Now, we don't need to know calculus to do kinetics, right? But I share this because if you're looking at this and you're going, what on earth is dA over dt? If this is new to you, right, we want to be aware that the equations are going to start to look a lot different. And the reason why I would have to use, for the change in concentration as a function of time, use a ratio more like this is because as I look at this, I see that there are changes that are occurring in the concentration of A as time passes. But the problem is that when I sit there and I go to try to take the slope or the tangent at any one of those given points, what I'm going to find is that as time passes, so does the actual slope of these tangent lines. And what that means then is that if the slope of these tangent lines represents at that moment the rate, like the instantaneous rate, again, this slope seems to be a lot steeper than something like that slope. And so this is the game that we're going to have to play when we talk about kinetics. We're going to have to understand, so what does my graph look like? Is it a straight line? Is it a curved line? Does it happen in a linear fashion? Is it going to be some type of accelerated or decelerated curve, etc., etc.? Now, before we get into all the math, and we're going to have to deal with a bunch of that in this unit, let's ask a more simple and fundamental question. Well, why? Why does the reaction occur more like what we're seeing over here, right? Why do they look more in this curvature instead of this nice straight line? I like straight lines. You like straight lines. I love this line. This is the best line ever. This is going to be simply y equals mx plus b. We were good with y equals mx plus b. Why on earth are we changing it? And the answer has to do with how reactants are going to work with one another or react with one another. And so to get an idea of this, let's look at a very simple scenario. And so let's take a look at the following example. Right? So here we have a simple chemical reaction. We have literally substance A is going to react with substance B. Right? Now I've drawn A as, let's say, these lavender little circles, and the B look more like these pink ones, right? Now here's the deal, right? In order to react, a little circle has to find the larger pink circle, right? Now, if I had to guess, let's say that I literally set it up exactly how you see it here. My guess is at first, it's going to be very easy for a lavender circle, the smaller ones, to find the larger pink ones. And the reason for it is because, again, let's say that everything is moving randomly, as they tend to do. At some point, I would expect that, let's say, this one's going to move in this direction, and probably this one's going to move something like that in that direction. And same thing over here, this one's going to move in this direction, and at some point this one's going to move something like that in that direction. Now you can see by this that means that off the bat, almost immediately, these two are going to find one another. And when they do, they will bond together to form C. Instead of C, let's call it, to make it a little easier, let's call it AB. All right, so AB is the union of the two of them. And so what happens? Well, initially this one, right, goes off and it finds this one over here, and now bloop bloop, they've bonded together. And so let's say we do the same thing over here. This one finds, let's say, this one over here, right? And now they've bonded together. But here's the thing. Do you see how I've kind of put them off over to the side? Did they magically teleport over there? And the answer is they didn't. What happened? When these guys bonded to one another, when they formed this new compound, that compound is actually now between everyone else. So again, let's pretend for a moment that this one is still traveling in this direction, and now this one's traveling in that direction, right? Like, let's just make it the easiest, happiest reaction ever. The two are going to run into one another, except instead of A finding B, what happens is that now they're going to actually run into a compound that's already created. They're not going to run it. A is not going to find B. A is going to find AB, and B is going to find AB. And ruh-roh, when they bump into this, you know what they're going to do? They're actually going to get pushed back out, right? They're going to get pushed in opposite directions. So notice, if we do this on a grand scale, it would make sense to me that initially, at the front end, particles are very quickly going to be finding one another and reacting, right? But within a very short amount of time, there's now all of these extra particles, these products, that are going to literally interfere with the reactants finding one another. And as long as they're in this interference, then that means that the reaction, tick, 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 slows down. So what's going to happen? Well, now, in order for these guys to keep reacting, we're going to hopefully have to wait for this one to kind of slide up, and this one maybe over here to slide down. And once that happens, now perhaps this one will be able to find that one. Emphasis on perhaps, because again, all of this is random possibility based on their movement. So if these two happen to be moving in the right direction, then huzzah! Look, they formed a new A and B. But what does that mean? Ruh-roh! There's now once again more stuff in the middle. So now this one comes this way, right? And this one might have been traveling that way. And notice that they're going to bang into a product, not necessarily the reactant that they were seeking. And so this is why, as time passes, we often see that a reaction will slow down, right? This is just one qualitative example of what's going on. There are other factors to consider, but for now, it at least gives you an idea as to why, as time passed, it seemed like the reaction started to take longer and longer and longer. The reactants literally just couldn't find one another. And the longer it takes them to find one another, then the slower they're going to make products, and the longer the reaction will take. So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.